Let's take a look at relativistic mass. And there are several ways of going about this derivation. This is just one of four that I will do. And so we're going to assume a perfectly inelastic collision. So we're going to do it from 2 points of view. In the S frame, we have A hitting B, and I'm assuming that B is at X is equal to 0. And they're going to collide in a perfectly inelastic collision, which means they're going to stick together. And so we have this combined mass traveling at some speed u. Also working under the assumption that the mass of A and the mass of B have the same rest mass. So the rest mass of A and the rest mass of B is equal to m sub 0. In the S prime frame, we can do it from the point of view of A. So A is not moving in the S prime frame, and that's at X prime is equal to 0, and then B is traveling to the left at some speed V. They're going to collide and combine into a combined mass of U traveling to the left at some speed U. And so it's just two different points of view for the same thing. I am going to assume that momentum is conserved at relativistic speeds. The Lorentz transformations, and there are a couple of videos I've done on that, as well as other resources, but we have the relationship between x prime and x and t prime and x and t. So this is in the point of view of the prime frame where A is at rest, and X and T is from the point of view where B is at rest. So after the collision, the combined object of mass big M is moving at a constant velocity u in the S frame or negative u in the S prime frame. So after some time elapses in the S frame, the combined mass moves a certain distance. Since it's traveling at a speed of u, this tells you the distance. Since x is equal to 0 at the point of collision, x is equal to ut. In other words, this is x final minus x initial, and I'm just saying the x initial is 0. So that's where I'm dropping my delta. So again, this is x final minus x initial, and x initial is equal to 0. So if I'm only dealing with one x, I don't have to write final since it's relative to 0. In the S prime frame, after t prime seconds have elapsed, the combined mass moves just in the negative direction. And I did not state this explicitly here, but yes, I did, with to the right being positive. And using the same logic, we have x prime is equal to negative ut prime. So now I bring in the Lorentz transformations here. So I have that x here is equal to ut, and then minus vt, and x prime should be equal to negative ut prime as figured out there. I can now use the Lorentz transformation of t prime and plug into here. So I now have negative u times t prime, which is negative u times gamma t minus vx over c squared, and which can then be written as this. So I have two different ways of looking at x prime. I have this, and then using Lorentz transformation for t prime, I can eventually get down to that. So equating these two versions of x prime. First off, over here, we have that gamma is equal to 1 over the square root of 1 minus beta squared, and then through various algebraic steps, you end up with beta as the square root of 1 minus 1 over gamma squared, and that will come in a moment. So beta is the speed relative to the speed of light, and so beta sub v is v over c, as opposed to beta sub u, if I had that, would be u over c, because I am dealing with two different speeds, and therefore there's two different betas involved. And gamma sub v would be when you're using beta sub v here. So from this equation right here, the gammas cancel out. I can factor a t out and cancel that out as well. So I'm left with u minus v is equal to negative u plus v u squared over c squared, distributing here. Getting it in terms of trying to solve for u, in other words, the speed after the collision, get everything on the one side, and I basically have set up a quadratic equation right here, actually a quadratic expression right here, which I can then set, if it's equal to 0, use the quadratic formula. And so just plug and chug into the quadratic formula. I get to here. And doing a little bit of manipulating, so factoring out the 4 here, so I have the square root of 4, which is just a 2. We get a bunch of 2's canceling out. I'm down to here, I'm dividing by this fraction right here, same as multiplying by the reciprocal, so that's why the v comes up on top. And then the square root of 1 minus beta squared is just 1 over gamma. And again, just algebra manipulations. Pause it if you need to. And ultimately, we come out with this plus or minus here, which means I have two different solutions. So ultimately, u is equal to v gamma sub v over gamma sub v minus 1, or v gamma sub v over gamma sub v plus 1. And so we need to figure out which one makes actual physical sense. And so I'm going to call this solution 1, solution 2. So let's just figure out if solution 1 makes any sense. So gamma sub v is greater than or equal to 1. U is undefined if v is equal to 0. Yeah, because if v is equal to 0, gamma is equal to 1, and I get 0 in the denominator. So there's one clue that something is funky going on there, but also this is dealing with a is not moving. If v is 0, a is not moving, and there's no collision going on. So that is, or in the S prime frame, b is not moving. But take it one step further. If v is greater than 0, then gamma sub v is greater than gamma sub v minus 1, because gamma sub v is greater than or equal to 1, which means that gamma sub v over gamma sub v minus 1 is greater than 1, which means that u is greater than v, because we have this expression right here, which we're saying is greater than 1, so u would have to be, it would be v times something bigger than 1. This would mean that when the two masses collide, they're going to gain mass and gain speed, because u is the speed afterwards and v is the speed beforehand of one of the objects, and that violates the energy conservation. So this solution cannot be valid. So solution 2 would have to be valid, assuming that there's not a mistake earlier. If v is much less than c, then gamma is equal to 1, and we end up with u being 1/2 v, which is the classical physics result, which makes sense that two objects of the same mass, one's at rest, another one hits it, the speed of the combined mass cuts in half, just conservation of momentum. But in any case, gamma sub v over gamma sub v plus 1 is less than 1, less than or equal to 1, therefore u must be less than or equal to v, and that seems reasonable. So we end up with that fact that u, the speed after the collision, is equal to the speed of the whichever one we're talking about before the collision times gamma over gamma plus 1, and so we have a solution here. Ultimately, we're trying to figure out the relationship of the masses, and so let's keep going. After the collision, we're dealing with the same situation, same as we had before. Before, in the S frame, A is traveling to B, which is initially at rest. They combine, so I have this mass of A plus mass of B at traveling to some speed u, and in the S prime frame, B is heading towards A. They collide and move on. So I'm going to start out with the assumption that the rest mass is conserved, and assuming relativistic mass equation. I'd have a little side note over here just as a recollection that if gamma is 1 over the square root of 1 minus beta squared, gamma squared is 1 over 1 minus beta squared. Not a huge math revelation there, I hope. I am making an assumption here, knowing what the final result is. I'll resolve that hopefully to your satisfaction later on. So if the rest mass is conserved with the relativistic equation, we have gamma sub v m sub naught v plus 0 is equal to gamma sub u m sub m, which is the combined mass, times u. So this would be the relativistic mass and relativistic beforehand of A or B, and relativistic mass of the combined masses. So if we assume that the big mass here is just the sum of the two rest masses, that's the assumption that the rest mass is conserved, and this equation becomes this, and m sub naught cancels out. So I have gamma sub v times v is equal to 2 gamma sub u times u, and so v over gamma u is equal to 2u over gamma v. Square both sides, we get this. Doing the substitution with beta, so I have v squared 1 minus beta u squared equals 4u squared times 1 minus beta v squared. Plugging in the formula for beta, which is just u over c. Beta sub u is u over c, and beta sub v is v over c. They're squared. And we end up with distributing on both sides. Bringing this over to the right, we get that equation, which those will combine, and we end up with v squared is 4u squared minus 3v squared c squared times u squared. Factoring u squared out, we end up with this, and so u squared is equal to, we now have u in terms of v, and so u is plus or minus this expression right here, and only the positive solution makes sense given the way that we've defined our variables. So if the rest mass is concerned that the big M, capital M, is just the combined two M sub zeros, then we have this is the speed after the collision. But before we derived this using conservation of momentum, and now are these two equal to each other? This, because we found this with the Lorentz transformation, this is U sub LT. We're calling this U sub CP. So if V is equal to 0, they match. If beta is equal to 0.8, they don't match. And so something is wrong there. We made an invalid assumption. And the invalid assumption is that the big M is M sub 0 times 2. So let's take a second assumption. Assume the relativistic mass is conserved. And so with conservation of momentum, we start out again with gamma sub v m0v is equal to gamma sub u big M u. And so big M would have to be equal to this. The alternative assumption is the relativistic mass is conserved. So gamma sub v m sub naught plus m sub naught is equal to gamma sub u big M. Factoring out m sub naught. And then we take this equation right here, plug it in for big M. We end up with this. We cancel out gamma sub u and m sub naught, and we end up with gamma sub v plus 1 is equal to gamma sub v over u, which ultimately, multiplying by u, we get this, and then solving for u, we get this formula right here, which is the same thing we got with the Lorentz transformations. So from that, it seems valid of our assumption that the relativistic mass is conserved, not the rest of mass. Let's see if we can simplify our formula for big M. So I have my two equations that we dealt with before. This is the one that we got from the Lorentz transformations, and this is the one we got from conservation of momentum. Plugging 4 into 2 here, plugging into U. So basically we're plugging this into there. We have big M is equal to, well, basically that with the new fraction in there, multiplying by, or dividing by a fraction, same as multiplying by the reciprocal, so this flips, and so that's where the gamma v plus 1 shows up on top. We have the m naught, the v cancels out, gamma sub v cancels out there, and we're left with this. Gamma sub u is 1 over the square root of 1 minus beta squared, or beta sub u, and if we keep going along that track, we end up with 1 over gamma sub u is equal to this big expression right there, which we will now plug in for 1 over gamma u here. And we end up with that. This factor cancels out. Go ahead and bring the c into, so that's c right there. That c is the square root of c squared, so we can bring that into the radical here, and the c squared cancels out from that. We get v over c quantity squared there, still to the 1/2 power. We simplify what's under the radical, and we end up with big M is equal to m sub naught times the square root of 2 times 1 plus gamma sub v. Let's see if this still matches our classical values, that if v is much less than c, then gamma sub v is roughly equal to 1, and big M is equal to 2 times m sub naught. Something seems to be valid there. Now, we did make the assumption that M is equal to gamma times m sub naught, and this is the point where hopefully I'm going to justify that assumption. We're still going to work backwards, and so instead of starting with that assumption, we will end with that. So we have our conservation of momentum, where m1 is equal to gamma sub v times m. We plug our equation 1 into our value for u right there, and so that's what that is. We then distribute, get our m1 terms over on one side, get a common denominator, multiply by that common denominator. We could have, instead of getting a common denominator here, it would have just been simpler if I just multiplied both sides by that factor right there, but I did it with an extra step. Now distribute the M1 to here and here. These two terms cancel out. I'm left with M1 is equal to gamma sub V M sub naught, which was the assumption that we had made before. Again, this is coming from conservation of momentum. This comes from the Lorentz transformation and conservation of momentum. But this idea that the mass is equal to gamma times the initial mass, where gamma is the Lorentz factor, comes from our assumption that momentum is conserved. And then we can generalize it that mass is equal to gamma M sub naught. I do want to point out at this point that there are some physicists who are perfectly fine with talking about relativistic mass, and others who say it's not the mass that's relativistic, it's the momentum. And, you know, to me, it's potato potato. I haven't run into a situation where this assumption as opposed to the other one, or this generalization as opposed to momentum being relativistic, not just the mass, or not the mass. I've not run into a situation where that's made any difference, and so I still stick with relativistic mass. And I've read one place that it's just a matter of when you learn physics that tend to talk about relativistic momentum, the older ones talk about relativistic mass. And that's it.